then whatever you see in the total will be against what we had in the syllabus. So I think that helps people understand a little bit better where their grades are, where they're going. All right. There were some questions on some of the workbook problems and some of the mastering physics. I think it's worthwhile to go ahead and go over those problems. If you turned in your workbook, that's great. If not, I'll collect it in a little bit. But on problem, which one was it? Problem 26-6. The question here is, for each of these figures, use a dot to mark any point or points other than infinity where the electric field is 0. So if you go far enough away, the field drops down, over the distance squared. So in some sense, at infinity, the field is 0. But we're going to not have to draw that on paper because that's really far and we need it to a big paper. But is there anywhere on the top one where the field might be 0? Let's think this through. If we imagine field lines coming out, or we imagine some field, the field leaves positive charge, it goes into negative charge. Let's look just at the top one at first. So if we look at field lines leaving this one and leaving this one, we have the field always to the left for both charges. And if we go to the right here, both fields are moving to the left. So the field from this charged body, the field from this charged body, they add up here, they add up here. But in the middle, they oppose. So maybe there's some place in here that the field is 0. Good. See how I picked where the region is? Now, if they were the same charge, where would the field be 0?
In the middle.
Right in the middle, right? But now we have this issue where this is Q, 4Q, and that's Q. So the charge there is 4 times as big. So there's a temptation to say the field's 4 times as far from this one as it is from that one. But how does field strength vary as we change distance and charge? The electric field is equal to K Q source divided by R squared negative vector for a point charge. So if we look at this, the field depends directly on charge and inversely to the square of the distance. So if we double the distance, what's going to happen to the field strength? 1/4. So if this charge is 4 times as big as this charge, we want to find a place where the distance is twice the distance from this one. So is there a point here where the distance is twice as far from the 4 and as it is from the 1? If we look here, we're 2 units of distance compared to 1 unit of distance. And we can make sure that these two fields are the same now by substituting. We can say E of 4Q equals K. Now our charge is 4Q all over 2D squared. And just look at magnitude. So we go to the right. And how does that compare to E1Q? That would be K times 1Q over 2 squared. Let's multiply this out. That's K 4Q. 2 squared is 4. D squared, 4's cancel. We can see the field strengths are the same. And we can look at orientations and see that field from the 4Q is to the right, the field from the 1Q is to the left, and so they'll cancel. See how we kind of reason that through? Now, we have the same thing here. We have 1Q and 4Q. So is the field 0 here? No, what's the difference?
Different charges.
One's positive, one negative. In this region now, the field is going from left to right because it's leaving the positive charge. It's also going left to right because it's pointing towards the negative charge. So the fields are in the same direction here, so they'll add. So we won't find any place where the field is 0 directly between the two oppositely charged particles. Now, if we go over to the left side, the field is leaving the positive charge. It's approaching the negative. In that sense, they oppose, right? So there'll be some canceling. But we are always closer to the 4Q than the 1Q. So the field from the positive charge will always be bigger. And so we can't ever get to 0 over here. Now, if we go over to this side, the fields are in opposite directions. When we're very close to the negative charge, the field from the negative charge will be much, much larger because the R gets very small and the electric field from the negative charge will dominate. In fact, if we get very, very close to this, the field from this will become negligible. Now, if we get very, very far away, all we see is a net of 3. And it looks like a point charge. If we get far enough away, we can't distinguish. There's just a positive charge of 3Q, and now we can calculate the field outlet. But somewhere in between, the two fields cancel. Once again, we want to find a place where we are twice as far away from the positive charge as we are from the negative. So if we go to, say, here, we're 1 away from the negative, and 1, 2, 3, 4 away from positive 4, so that doesn't work. We go here, the distance to the negative is 2, 3, 4, 5. 5, that's not 4 to 1. We go to here, we're 1, 2, 3 away from the negative, excuse me, 2 to 1. We're 1, 2, 3 away from the negative, and 6 away from the positive. Now we're twice as far away from the positive as we are from the negative. Since there's 4 times the charge, that will be where field is 0. Again, we can substitute in. Now we're going to have a 3D squared for Q1. We'll have a 6D squared up here. But if you go to the map here, is there questions about how you reason through that? No response. You can do it algebraically, but I like to reason through. That again. Any other questions about the workbook problems? On the dots, I do want to check this. Is it possible to have we have a charged particle here. We have another. Is it possible to have that?
No.
Why not?
The magnitudes would have to be the same.
The magnitudes have to be the same. Remember, Newton's third law still applies, even though we're in physics 2. So if the force on body A due to B is 10, then the opposite will also be 10 direction. Question?
Do you have another charge on the right side? Would that allow?
If we have another charge, that would allow things to be different. Yeah. But if those are only 2 charges in our universe, now, if there, that's a good question though, I like this. Let's say there was another charge over here. can the force that this particle, let's call this A, B, and C, how does the force A exerts on B compared to the force B exerts on A once we add particle C?
They're still equal.
They're still equal and opposite, right? So we could have this force and this force, they're equal and opposite. That's B on A on B. But now, let's look at the forces from C might exert a force on A that looks like this. Let's see if I can find another color. Yeah. Okay, go ahead, go with red. And then between A and C, there might be a force that looks like this. So the force A exerts on C equals the force C exerts on A. So each pair is the same. Now, when we add them up, the net force on A now, when I add this to this, the net looks like that. The net looks like this. And the net looks like that. So the net forces look different, but each pair of forces is equal in magnitude in opposite direction. Then it's an important distinction. All right. Any other questions? Any questions more about this? The questions I had heard, and then this one I just wanted to double check. How many people have trouble with this one, or are having trouble? Quite a few. All right. So there are several ways to approach this. I can show the approach from that I taught, and I can give you, and I can kind of parallel the way Knight teaches. How do we approach this problem? We want to find the field at the black dot due to those charges. So let's see, which of those charges are source charges? Which ones of those are we considered creating a field? Are the two 10 nanocoulomb sources? What about the 5 nanocoulomb? They're all source charges, right? We're looking at the field at the dot, so all the charges will be sources. If I wanted to know the force on the 5 nanocoulomb charge, would that be a source charge now? No, it would be the charge of injury. The first thing you want to do is separate who's the source, who's the injury. In this case, we're asking for the field at this point. How do we go about finding? We know that our field will be equal to K and our source charge. Actually, we're going to sum these up. We know K is a constant. We can find the charge for each of these. The real challenge is finding R hat and R squared. I like to use R hat. Knight doesn't necessarily use R hat. So let's go ahead and do it my way, and then I'll show you very quickly how Knight would approach it. We need to find, the way I start things, we need to find the vector R. The vector R, let's look at this charge down here first. So I'm going to analyze, let's call this A, B, C. So we're going to look at B. And so for B, we have 10 nanocoulombs here. We're move 4 centimeters to the left. Move 2 centimeters up to get to our point of interest. Let's call this the x-axis. Let's call that the y-axis. Where's the vector R? Where do we start? What are we at? If you don't get this, the rest of the problem just goes to heck in a handbasket. Is this R? Does it matter? It's extremely important to go from our source to the point of interest. That could be the, if it's Coulomb's law, it's from our source charge to the charge of interest. All right. How far do we go in the x direction? 1, 2, 3, 4 in the negative direction. And how far in the y direction? 2. 1, 2. And our units are centimeters. Once we get this, the rest of the problem is really plug and chug. This is really the key to the problem. Identify our source, draw our vector from the source to the point of interest. Everything else now can be derived from our formula. We know Q is 10 times 10 to the negative 9 coulombs. Once we know our vector, we know K. Once we know our vector, we can find the magnitude of our, and the unit vector, our hat. We can substitute in, and we're done. So, what's the magnitude of R? The square root of 4 squared plus 2 squared centimeters equals the square root of 20 centimeters, or if you want, 2 times the square root of 5 centimeters, or 0.025 meters. What's our unit vector? Divide this by that. Negative 2 over root 5 I hat plus 1 over root 5 j hat. Divide r by r hat. And now we can substitute in. Times 10 to the 9th, isn't it? What is it? Newton meters squared per coulomb squared. That's K times Q. Divided by Now, we can multiply this out to get the I hat, multiply this to get the j hat. Then we have the vector, or the field in I and j components. When we do the other two charges, it's a lot more straightforward because they're just in the x and y direction. How would Knight approach this? What Knight does is he doesn't worry about how we draw R. Knight determines R equals the square root of 2 centimeters squared plus 4 centimeters squared equals the square root of 20 centimeters. He then calculates the magnitude of E equals K times Q over R squared. So notice this will be equal to this. And then he said, what direction is this field? He then figures out the direction here. So he'll figure out that angle. And then he'll break E into its components, and we'll get the same, and you should get the very same components like that down there. Are there any questions about this? I promise you that you'll see a problem that looks either like this or like Coulomb's, or like just a fourth problem. So I guarantee you this will show up in the test.
So the actual charge is actually the product or is it just the physical analysis that I
Okay, so the question is, how does the charge change things? If you use my method, the charge here will change direction, will become negative if it's negative, and that will change the direction of the field. So if we look at this very same problem, and the charge was negative, then the x component and the y component will not change signs because we've included a negative sign. In Knight's method, since we're just calculating a magnitude here, really he does this. Now you have to say, oh, this is a negative charge, so this field is towards the charge. So if you use Knight's method, you say, okay, now that I've calculated the field, I now know that it's pointed this way. You might find this angle and break it into components. But if you do it this way, the method doesn't change. The only thing that happens is you use a negative charge here. So you have a negative inside the equation. You, for example, in the x direction now, instead of having a negative, you'll have a negative, and the negative becomes a positive. The rest of the problem, once you know the vector E, the rest of this is really vector manipulation. Once you know EX and EY, you can substitute them. How do you find the magnitude of E? Question?
I have a question on the first one, so you can finish.
On this here?
Yeah. I was wondering why you used that 10 as the source instead of like the other ones.
just to show.
I'd have to do all three. So I find this answer, then I do the answer for the other 10, I do the answer for the 5, and then I have to add those vectorially. I need to add up all the I components, I need to add up all the J components for those three fields. Because all three of these charged bodies contribute to the field at the point. So this was the hardest one to find because it's not in just the Y direction or not just in the X direction. So I did that one because I think it's the hardest of the three. So if you use the method I taught, you don't, if you start your R vector always from the source to the point of interest, you make sure that you carefully track your signs. everything should work out. If you use Knight's method, you find the magnitude of the field to meet the source charge, then you have to be very careful about the direction to break that magnitude into its components. In both instances, you end up with a field with the components in either the x direction or the y direction. You need to add them up to find the total field at that point. I promise you, get this skill down. I promise you it's going to show up again. And there's just, you will see a problem that looks like this. There will be charge, I'll ask for the field at a point, or I'll have a charge of interest, I'll ask you to force. I'm going to do one of the two. I can do both, right? Really, once you know the field, if I now put a charge here, how would you solve this problem? I ask you to find the field. Now you know the field, and now I put a point here. Will you now use Coulomb's law to find the force from this, plus the force from this, plus the force from that, and add them together? No, what's the much better way to do it? Q times Z. Once we know the field at that point, if I put a charge there, just multiply that charge times the field, and you're done. That one looks right. We know once you know the field at a point, I'll ask you if I put a charge there, what's the force on it? Multiply that charge times that field, and you're done. Don't make it any harder. So if you've already calculated the field at that point, you know what to do, right? Star that in your notes.
What does that find? If you multiply the charge by the field?
If you know if this is the field at a point, so if I place this charge at a point in space that has this field, that will be the force on that charge.
What does it say after the charge is placed?
At a point. At a point. So this is at some point in space. I put a charge. The field is something. If I put a charge there, the force. Now the field might be different down here. So if I move that charge down here, the different field, different force. So I can't just pick the field at any point in space and multiply it times any charge and get anything of meaning. I need to find the field at the point where the charge is, and that tells me what the force is now with that charge. We need to separate what's our source charge, what's the charge of interest. All right, so once we know the components, you should be able to find the magnitude, and once you know the components, you should be able to find the direction. How many people like spending this much time reviewing homework? Some people were kind of ambivalent. People thought it was a waste of time. There's a mix, but there's. All right. I want to talk about. So what I did want to do, if I didn't go over homework problems, I wanted to talk about different source charges. We spent a lot of time talking about point source charges, but I would also make sure that you know if I have a long line of charge, we can use the equations to find the field from that long line of charge. If I have a plate of charge, be able to find the field from that plate of charge. If I have infinite plane, a long wire, and a point charge. Could you find the field at a point in space? Use Coulomb's, use this equation for a point source, find the field from the point source, and you use the distance from the wire, find the field from the wire, and you use the equation for the plate to find the field from the plate at that point. You add those three different contributors to the field, and that will tell you the total field at that point. So, this is hard, right? If we now have a shape, and we have an infinite number of charges, if the charges spread over, I showed you that we can integrate, and I spent some time setting it up, but I didn't actually do the integration. You can see the integration in the book. If you're going to go on in physics or engineering, you probably should do a couple of those. In practice, I think I've thrown some in the bonus problems. They're good problems to review, but there is another way to approach determining the field. That's this whole sense of Gauss's law. And what it requires is that we look at our fields instead of as points and the field vectors at different points in space. We're going to replace those field vectors with field lines. Field lines start at a positive charge, and at every point on the field line is directed in the same direction as if we placed a field vector at that point. And that field line will continue until it runs into a negative charge. The exception would be if we have a point charge and it's the only charge in the universe, the field lines all move out from that point charge and they go to infinity looking for the negative charge. But in reality, there's a balance, so someplace they'll start to bend out towards wherever the negative charge is. If we have a wire, a long wire, the field, imagine this wire is infinitely long. The field will stick out from that wire. Now, is it possible if this wire were very, very long for the field to point up? Why would there be a preference to pointing up to down if this was infinitely long? It wouldn't make sense. I'd turn it over, the sense of symmetry. Now it's pointing down. But why would that happen? If this were infinitely long, we'd need some type of symmetry. So that it doesn't matter whether we flip it over or not. Now, if the field lines were out, you see that in an argument of symmetry, the field has to be sticking straight out from that wire. If we have a infinite plane, like the wall, this plane went up and down forever, went this way direction. It looks the same in all directions. The only way for this to have symmetry is to stick out straight from the wall. It would make no sense for it to have a preference to the front or to the back if this plane were infinitely large. I'm going to skip that. So our field lines, all right. So we can imagine our field lines, they start at positive charges, they go to negative charges. If we look at the field looking at our point, what do we notice about the density of the charges as they leave the point charge? Can you see that the field lines will spread out? Where the field lines spread out, the field is weaker. We move the point away from the point charge, the field lines spread out, the field gets weaker. Where the field lines are more dense, the field strength is stronger. If we have an infinite plane, we can imagine the field lines coming out they're uniform and there's no preference to up or down. Since this plane is infinitely long, the field is perpendicular to the charged plate, and they go on forever because this is an infinitely large plane. Now, reality, if we get far away from a real surface, it's not infinitely large, it'll start to be curvature. But when we're very close to a very large plane, or relatively close to any plane relative to its size, the field will be uniform and leaving. Just like the gravitational field on the Earth, it's uniformly down. Now, to understand Gauss's law, we need to introduce this concept of flux, which is the number of field lines that go through a surface. So we started off with, on Monday, as we imagined a box. And if I build a box around this charge, the field lines go out through the box. And if I just showed you, I cut away, and I said, what's in the middle there? And you say, oh, there's obviously a positive charge because I see all these field lines coming out. Or if I saw more field lines going into the box, that would imply what type of net charge was inside that box. Negative. So this, if we count the number of field lines, that gives us an idea of what the charge is inside. What I'm struggling with trying to show you is that if the area looks like this, and the field lines are going straight through, we can count the number of field lines by saying if we have 6 field lines per square meter, and we have 2 square meters, then we're going to have 12 field lines going through that area. But what happens when we start to change the orientation of our surface? So this is our window, we're counting the number of field lines going through. If it's perpendicular to the field lines, we can see that field lines go through. What happens when we're perpendicular? How many field lines are going to go through this plane now? Can you see that it's none? And if we're at a 60-degree angle, we'll get more than none, but less than 100%. So that's what I'm trying to get at in this picture here. We have field lines going from left to right, and one of the field lines is falling off. And now I've switched the orientation of my plane, so it's not perpendicular. I'm going to define this plane with a vector, an area vector. This is a new concept for a lot of us. And our temptation would say is, well, the area, the plane's defined in this plane, right? This plane here. But how many vectors can I draw in that plane to define that area? There's an infinite number of vectors in that plane, aren't there? How many vectors are perpendicular to the plane? There's only 2, right? One in, one out. So when we have an enclosed box, we're going to define the positive direction for the area as going out. If it's not an enclosed surface, we're going to have to define whether it's, in this case, to your left or to your right. But once I've said, this is my vector, there's a plane that's perpendicular to it, there's no question what that plane is. If I say, so we're going to define area vectors as having a magnitude equal to the area of interest in a direction that's perpendicular to the surface. When we do that, a very nice thing happens. So this is the direction of our plane. My fields are falling out. Here are our field lines. If the area is perpendicular, the surface is perpendicular to the field lines, the area vector is parallel to the field lines. You see that? If our plane is no longer oriented, I can now look at the angle. So here's our area. Our field lines are perfect. There's an angle between our field lines and our E and the area vector A. If we look at our area, if we take the cosine of that angle, doesn't that give us, so now we have that angle there. If we look at the cosine of that angle, let's see, now I'm just gonna draw the board. Imagine our surface looks like this. Area vector perpendicular field lines are moving. Is that not cosine theta of this triangle? So if we take our A vector times the cosine of theta, that's the right thing. Isn't that the portion of that area that's the field lines are going through? So it works out that the flux, the number of field lines going through this surface, will be A times E, the number of field lines, times the cosine of theta, or we could say E dot A or E dot B. It's a real long discussion to try to give you a physical sense for why this is a dot product. So our phi is our flux. It's like the number of field lines. Then A is the area, E is the electric field. So if we have a uniform electric field, we have an area, the number of flux, so the number of field lines going through that area tells us the flux. If we know the total flux from an enclosed area, that tells us the charge inside. So if we enclose a region of space, we count the number of field lines going out, or if we measure the flux, that tells us the charge inside. That's true no matter what the shape of the surface area, doesn't matter how the charge is inside, the net charge divided by epsilon naught will always equal the flux through that surface. And that's a very powerful law. So the key issues here are that we look at the net flux. So there could be flux coming in the surface, there could be flux coming out of the box. But if we add up all the total flux coming into that box, that will always equal the enclosed charge divided by this constant called epsilon naught. So if I tell you the flux is 10, whatever the units are, can you find the charge inside that box? You multiply by epsilon naught. If I tell you the total charge inside of a volume is 2 coulombs, can you find the total flux leaving that box? You divide by epsilon naught. It doesn't matter what the shape of the box is, it doesn't matter what the distribution of the charge is, this is always, always true. Now, what I'm going to show you is if there's symmetry, and if we choose the right shape, then one, the math becomes very easy, and two, we can discern a lot about fields that's very, very useful. I feel like this isn't as going as exciting as I hoped it would be. Now, I want to warn you that the calculus, the math to calculate, the problem is if you look at an arbitrary surface, the field changes at each point in space, and the orientation of the surface changes at each space. So what we have to do is to find the total flux. We need to add up all the different infinitesimal areas around that surface. And what we end up with is an ugly, ugly looking integral. But if there's symmetry, that integral becomes algebra. So I'm going to show you an ugly integral. Don't panic, because we're going to explain it and we're going to be able to solve it using algebra. Now when you get into the future and after you've taken Calc 3, you can solve this thing. But for now, I'm just warning you, it looks ugly, but it's not that bad. We start out with the total flux leaving our enclosed area is equal to the total charge inside divided by epsilon naught. We can calculate this flux if we look at the electric field at each infinitesimally small area and integrate. The circle here tells you that that's all over an enclosed volume. But I'll show you some ways to do this. It's really not horrible. Right? So it's ugly, but let's get away from it and start looking at how we're going to resolve this. Imagine that we have the electric field leaving this source charge. Right? We're going to just look at a point charge now. The electric field lines all go out vertically. So it's pointing out. You can imagine that this is a sprinkler head with holes in it that's under high pressure, so the water's squirting out in all directions. And that's kind of like the field lines. What we want to do is put a sphere around this and count the number of field lines that leave the charge. So if we totally enclose this source with a sphere, we're going to count all the field lines that leave it. If this point charge is centered inside that sphere, what do we know about every point on that sphere that's surrounding it? Isn't the distance from every point on that surface equal to every other point? So from the source to every point on that spherical surface, it's the same, right? So by symmetry, we'd expect that the field would be the same at every point on that sphere. The other thing is, imagine we have the surface out here. If we have a sphere around a point, isn't the field perpendicular at every point? So all that time I spent talking about the dot product, we don't need to worry about it because our surface will be aligned with the field. So the dot product will just be 1. So we now know the surface. So if you look at, we have a point charge where some arbitrary little infinitesimal, the area vector for that little teeny vector is out. The electric field is out. So the dot product is just dA times E. And now when we integrate over the surface, we'll just need the surface of the sphere times the electric field at that point. And that will calculate that ugly integral that we have up here. We just need to do a product of the field strength times the area of the surface. So we're just about out of time. What we'll find is, this is pretty straightforward. We're going to do a similar thing with a wire. If it's a very long wire, instead of putting a sphere around the wire, we're going to put a cylinder. And we'll look at the field coming out through the sides of the cylinder and through the ends of the cylinder. And we'll take that up on Friday. Maybe I should have just jumped in instead of doing things rather than trying to explain the flux. But